21, and this is Synergetics stream number 12. Looks like everything is working. Today in Synergetics number 12, the spirit for today is reformat, partition, and listen. Today in 12.0, we're going to go over some key memes and themes, then the things to integrate, and go to some text readings. There'll be two sections of the text readings. The first is going to be a second session, I guess, on cosmography with a focus on the rhetoric of the tetrahedron, the tetravertexion. Then the second half of the text reading will be section 200 in Synergetics, narrative exposition of spherical accommodation. We can start with just some of the key memes and themes of Synergetics. Synergetics is relational and multi-scale thinking. We're going to come back to that multiple times today. It's connected to accessible experiences. In Synergetics, there are no infinitesimals or points, lines, planes, at least in the traditional sense, but we'll come back to that in the rhetoric of the TET. Synergetics frames design as anticipatory cybernetic science. And there's this relationship between the applied tensegrity and the theoretical synergetics, somewhat like the applications of engineering and the theory of physics. But the big ideas, of which there are multiple, one of them here is that space has a shape, and it's a very specific shape. Universe is the total scenario, and it doesn't need a the because it's the only one, whereas system is any specified subsystem, which implies that it must exist, ergo it has to have geometric spatial properties. And there's this 4D meme that we see from the beginning onwards that has to do with a few different senses of thinking 4D, including 4D time lock, a tetrahedral focus, which is one of the main parts of today, as well as other ways that 4D is playing out. On the key memes and themes, I think it's been mentioned on the stream before that TrimTab was being asked about some big ideas to compile. So here's an email from Richard Ramsey. Hope it's okay since it was a public mailing list on October 7th. And Richard wrote, I tried my hand at mapping the big ideas on my whole system mapping framework. I worked off of a recent set of slides used for a suicide prevention workshop in a curriculum design project. So Richard's really cool and insightful person and has a lot of experience with applying synergetics in social contexts. So I thought it'd be cool to, with credit, show some of his ways of reorganizing the big ideas that TrimTab Reading Group had come up with help from Kurt and others. So the orange is the design science methods, DS, design science. Yellow is the design systems change. The gray triangles are the design science system. And then the blue is the person. And so these are some of Bucky's big ideas. Like here it says guinea pig B. That's one of Bucky's nicknames for himself because he was just saying how he was always experimenting with himself, seeing what a regular person could do. So this is kind of an idea of him as a person. And that's a few other points here, like Applewhite, the collaborator on Synergetics project. Whereas in the methods section, just like a paper, we see some of the methods like Tensegrity, linear, nonlinear systems, TrimTab, a lot of related topics there. So that's pretty cool, like a geometric way that Richard generalized from his work in the social context. And then here's a second image that's kind of unpacking it. So it's those four areas, and it kind of is like a tet of tets, which is something that we're going to come back to again later. But each one of these has like multiple sections, and just showing how do we represent Bucky's big ideas, because they're so big and there's so many of them. So how do we, and some of them have been accredited to him when they shouldn't have been, and vice versa. So how do we really know what to summarize Bucky's work with? Thanks, Richard, for the really cool, though, images. Thanks for sharing them. All right, and the things to integrate hasn't really changed that much. So anything that people suggest here or in the YouTube live chat, I'll be watching that. Just we'll integrate it later. Okay, well, the first section is going to be pulling from mainly chapter 6 of cosmography, and it's going to be called Rhetoric of the Tet. So this was a list I compiled yesterday when rereading Cosmography, the book, chapter 6. And just to refresh on the book itself, so the book is written with Bucky as the, I guess, big font author, and with Kuromia as an adjuvant on the cover there. And it was mostly written before Bucky's physical death in 1983, but then it was revised and published later. So it was kind of a posthumous collaboration. That's why it's called a posthumous scenario. And in Synergetics Stream 10, there was some discussion on the earlier chapters. This is going to focus pretty much on chapter 6, which is a longer section with a lot of images. And also thanks to Brett for digitizing this ebook, letting us use it for education. So when reading chapter 6, it just struck me that there were so many ways that the tetrahedron, the tetravertexion, here's my desk tet, as I sometimes show. There were so many ways that the tet was being deployed and justified and utilized. And so this is a totally partial list. It's not all of the mentions of the tet or uses or implications of the tet in chapter 6 of cosmography, and certainly not the full set. And so that's why I chose 15 to stop at, because we saw earlier that there was this 4 times 4, a tet of tets. The tet of tets is 16. So 15, incomplete. 5 times 3, incomplete. There's more to be added. This isn't even all the tet memes we've previously talked about on the stream. But there are definitely 15 things about tets that people might not have expected to be playing out in Synergetics the way that they do. So here I'm just going to read the 15 points, and then the next slides are going to go through each point and use an image or some text from cosmography to show about why it is that way, or just something that lets us do. So tet is in tetrahedra. It's a long word. It means 4 faces. Tetravertexion is also equally appropriate. It means 4 vertices. And it's a long word either way. So we can just go with tet, and that's the shape down here on the bottom. So tet is minimal space enclosing 3D existing system. Tet has multiple physical realizations. Tet has omni-triangular stabilization. Tet has 4 faces, 6 edges, and 4 vertexes. Tet densely connects 1, 2, 3, 4, 6, and 12, and 24. Tet world can make cubes, but not vice versa as well. Tet can handle powers of numbers as well as the cubic paradigm can. Tet is the minimal geometric and topological system, so it's an interaction model. Tet is a mnemonic for phase change. Tet structures of tunable frequency can make points, lines, and planes. Tet tensegrity analysis gives a natural model of function, constraint, and nesting. Tet great circles eliminate the need, not the existence, for pi. Tet, just one, is hiding inside of every closed object or system. Tet accounting is clean for angular, general, length, and volumetric measures, which are specific. Tet invariance group equals best invariance group. All right, well, let's see about this list. And of course, this is just a work in progress, just like all these streams are. So if people have other parts of the tet that they love, or they don't think that one of these are relevant, just let me know in the live chat, leave a comment. So first 2. So tet is the minimal space enclosing system, and the tet has multiple physical realizations. So the minimum system is in figure 6.4. So when there are 4 events occurring, 4 parts of a system, it is the first shape that separates insideness from outsideness with a betweenness reflected by the face. So there can be the minimum system of an atom existing sort of by itself, not interacting. Okay, cool story. There's the story of the dyad. There's the story of the triangle. Those are all conceptual. But the first system that starts to take enclosing space form in the real world, not to say that the metaphysical isn't important, but in the physical world, is the tetrahedron. So it takes a special place as the minimum polyhedra and the minimum system. That's the first point. So why go with the tet? Why go tet first over a cube first or over some other shape? Well, it's the simplest, smallest, first one that can exist in 3D. Second point, tet has multiple physical realizations. So this is from figure 6.13. 3 ways of physically demonstrating the simplest system in the universe, the 4-vertexion, tet-vertexion. The tetrahedron, tetravertexion or 4-vertexion, can be equally validly drawn as 1. The Platonic solid emphasizing the 4 faces, which alternatively are known in Synergetics as divergent openings. So this is the traditional Platonic tetrahedron, it means 4 faces. So that's 4 faces of the tet. Alternatively, we can think about it in terms of the 6 lines or edges, which are known in Synergetics as vectors. So here we're seeing this as sort of energy vectors connecting energy events, which can be attractive or repulsive, like gravitational or radiational. And then the edges connecting the events are energy vectors. And then there's a third framing of the tet, which is the vertex domains, which alternatively are known in Synergetics as the closest packing of spheres. So here's a few different framings. We can have the face-centered understanding of the tet, which has this folding and unfolding ability, as shown in the 6.13. There's this edge model with like toothpick model of the tet, and it takes 6 edges. And then there's the energy event, either radiating or gravitational event, or the close packing of spheres, which is shown here. There's a few other representations that look pretty cool that are in cosmography. So here's the folding and unfolding. This is the involution and evolution of a tet. So it starts folded, and then it opens at the one corner and folds through flat, and then it reformats the other way, which is analogous to, in 2 dimensions, what a triangle can do. So that's pretty cool. And then here is a connection in a figure 6.59, 4 vectors of restraint define minimum system. And it goes through, this is not very clear on the video probably, but wind instruments looks like kind of a pendulum. This says string instruments on a plane, drums, kind of like a tension system, and then gongs. So this is kind of cool thinking about what sound does the different constraints make in a tet. So very flexible of a shape. You can think about it as the centers of spheres that are close packed, the minimum faces, the minimum edges. There's a lot of ways just to get at the tet. So those are points 1 and 2. All right, point 3 and 4. So points 3 and 4, we have, so that will change the numbering. So tet has omni-triangular stabilization, and tet has 4 faces, 6 edges, and 4 vertexes. So first for point 3, figure 2.7. Here is a tet with all of the triangulations drawn with the octahedra inside of it. And so I'll read the caption. The 3 great circle-spun square planes exactly bisect the tetrahedron in 3 symmetrical ways. Note the primary tetrahedron and the secondary internal octahedron, and only then are the implied square cross-sections of the octahedron apparent as tertiary derivations of the primary structural system, the tetrahedron. There is no single plane, omni-equal angle, equal edge square structural integrity in universe. Squares and cubes are always and only tertiary derivations of prime vectorial structuring systems. So that's going to be a theme we return to, which is that if we look at structure empirically, we find that in planar systems, the triangle is the unit of structure, and in space enclosing systems, the tet is the minimal unit of structure in terms of what can be supported from a system resilience and stability perspective, whereas cubes are always emergent at larger spatial scales or in derivative form relative to the structural stabilization of tets. So one advantage of the tet, point 3, is that it's all triangular all the time. Whether it looks like my desk tet or another tet, it's all triangles, so there's no need to entail some other level of structure. We can just take the system as its own unit of structure, because triangles and tetrahedra are the minimal units of structure in 2 and 3 dimensions. Point 4. Tet has 4 faces, 6 edges, and 4 vertexes, or vertices. Bucky kind of different times in his life probably used both words. So just looking at the number of faces, edges, and vertices. First, there's the relationship of the faces and the two-ness, which we won't even go into. So there's equations that relate these 3 columns to each other that are very important, that hold for all shapes. So that puts them all in equal grounding. But just looking at the numbers here, it's pretty clear to see that there's fewer faces, fewer edges, and fewer vertices. So this is like getting the minimal system. It's just parsimonious. It's going to not require any second level explanation for why we don't want the tetrahedron. It's just the default choice. It's the smallest one. That's point 4. Okay, point 5. So point 5 is tet densely connects 1, 2, 3, 4, 6, and 12, and 24. Okay, so this is a little bit of a numerology discussion, but it relates to the geometry and the relationship between the tet and the oct. So here we saw the oct implicit in the tet. One way that this is facilitated is that the 6 edges in the tetrahedron can be thought of as analogous or corresponding in space to the 6 vertices of the octahedron. This is a consequence of the fact that the octahedron can be inscribed in a tetrahedron. The 6 edge midpoints of the tetrahedron are the 6 vertices of the octahedron. And then there's more information, a few links. So here's where that comes into play in cosmography. Okay. All right. So here, 6-dimensionality of both tetravertexion, the tet, and its contained hexavertexion, the oct. So here are those 4 energy events, the 4 corners, the static somethings. Then there's the macrocosmic tetrahedron, outsideness. It describes the maybe even Markov blanketed or just the external system. Then there's the octahedronal microcosm with insideness. This is the shape rattling around inside of the tet. And then this is being related to thought, with thought tuning into the relevant wavelength. So this is just one way that we're getting that 4, 6, 4 of the faces, edges, and vertexes, but also getting the faces, edges, and vertexes of the octahedron, 12, 8, and 6. And then 8 kind of comes along when you get 2s and 4s. So I didn't write it as a tenet exactly, but it's relevant, but it's kind of 12 and its divisors as well. Like 1 and 12, 2 and 6, 3 and 4. So this relationship allows a lot of jumping around between different shapes, because it can be like, okay, well, here's the points of the 6 vertices of the octahedron. And now those are going to be the midpoints of the edges of the tet. And then that's going to do this. And then that's going to divide and go over here. So you can kind of hop around the system based upon where there's overlap, like a train station. All right. Then here is another where it connects to 24. So here's that tet in A. And figure 640. The tet, the quarter tet, which has 4 congruent shapes that look like they have a reduced height, but a a broad base, then those get divided into another tet. And that becomes 1/24th of a tet, which is called an A module. So that's a pretty cool thing. Like the tet subdivides to a tet, and I guess that's where the buck stops. But somebody else probably knows more about that than me. And then just these are kind of thought questions. Like, what is the consequence of this deep linking of 1, 2, 3, 4, 5, 1, 2, 3, 4, 6, sorry, 8, 12? What connections can we make? And then the question, where are the 5, 7, and 11 nisses in the system? I know there's people who have a lot of different thoughts about 5, but 7 and 11, also maybe prime numbers. Where are those in the system? Do we need them? And then 9 and 10, which are not prime numbers because 9 is like 3 times 3, and then 10 is 2 times 5. So where are those in this system? Where's 9 and 10? How do we get 9s and 10s? Do we need them? So that's point 5. That the tet gives us this nexus, like a mnemonic or a lobby, where we can come to the tet and then pop off towards a different direction, like a number, like 12, and then go from 12 to 144, and then divide by 2, different number transportations. Okay, so now point 6. So point 6 is tet world can make cubes, but not vice versa as well. So remember, first there's this oct in the tet, and then that relates to here. Squares and cubes are always and only tertiary derivations of prime vectorial structuring systems. So one way we get the cube is from the oct with the faces that it defines, and it itself is inscribed inside of a larger tet. So that's this, remember the oct in the tet. But also this kind of tet above, tet below system, the star oct. These 6 points end up inscribing the tet. And here's the quasi-cube as well. So one way to think about it is if you have pixels, you're always going to get pixelated tets. No matter how large you make the tetrahedra, there's going to be a ragged pixelated edge. And then you can interpolate it and try to make it smooth with high resolution. But the tet gives us a natural way to form cubes in a tet first world, whereas the cubes don't give us as natural of a way to form tets in a cube first world, which is something we're going to return to. Because here, the corollary of that decision, so let's just call that decision whether to go tet first or oct, or tet first or cube first. Let's just call that decision cultural. The corollary of the decision is that in the tet world, when things are tet first, the cube is the odd fellow. So here is figure 6.73 in cosmography. It's the cube stabilized with a tetrahedron. Why is that a valid decision? Why is it okay to cross? So that's 1, 2, 3, 4 that are being stabilized by triangles. And then there's one going the other direction, covering the other bases. Well, you need that. If you're building a house that looks like a rectangle, you need that cross bracing for structural stability. So it's not just a nice coincidence, it's actually an implied structural consequence of a cube. So here, in this table, it makes the area over area squared look very clean. It's like it has a volume of 1, it has a surface area of 6, so that's pretty clean. Whereas the other shapes have kind of strange relationships. So that's one way to, in this cubic world, to talk about these numbers. So it's not like they're bad, but they have some decimal points. But later, as we see, if we multiply by these Dymaxion constants, which we're going to come back to later here, as well as in the narrative exposition at the end, 200. So if we use this linear area and volumetric, so first, second, and third power relationships, and we say, okay, the tetrahedra, we're going to say it has 4 faces. It has an area of 4. I need to buy 4 triangles of paint to paint my tet. It takes 1 unit of brass. Thanks, Trevor, again, for this beautiful desk tet. And then the edge amount is going to be 1. It could be a 6, but we're just going to renormalize it to 1. So in this world, where we've converted according to the Dymaxion constants, we see that the octahedron has a clearly revealed volume of twice that of the tet, with 4-fold volume and the same edge length, edge ratio. So we can see cube now stands out as the one where the edge is something like root 2. But what's interesting is it has an integer volume of exactly 3. So just like there's an incommensurability, it's clear that we're either going to renormalize to the cube and then have a lot of irrationals in other shapes, or we can have a lot of integers for most shapes, many shapes, tet shapes, and then the cube has some nice properties like a volume of 3 on the dot, and then a few weird properties like its edge, including the root 2. But again, we're going to come back to that. And so it's just to say, like, you can't have both be integers because they're clearly not on the same meter stick. Let's go with the tet having the nice values. And then the cube will just have some quirks, but that's okay. It's a quirky shape. And then here's another relationship with a cube. Like, a cube may be formed by placing 4 1/8 octahedra with their equilateral faces on the faces of a tet. Since tet volume equals 1 and 1/8 oct equals 1/2, the volume of the cube will be 1 plus 4/2 equals 3. So that's sort of a first principles, operational, constructivist proof, proof by demonstration of rebuilding a cube of volume 3 nucleated around a smaller tet. So just anything that people have nice to say about cubes, let's let it be said, but also recognize that it might derive from a downstream or upstream tet. 7. All right, so 7 says, tet can handle powers of numbers as well as the cubic paradigm can. So sometimes when people are learning about tet and the quadrats in the school of tomorrow, they might think, well, how could we ever get rid of squaring a number or a number cubed? 3 cubed or 2 cubed, 2 squared. Isn't that literally just 2 by 2? Isn't that literally a square number? So here, and then here's a physics interpretation. It's not just Connect 4 where you are squaring numbers. This is in cosmography, talking about gravity. The system component intertensioning, so thinking about gravity in terms of tension as opposed to compression, tensegrity, always conforms to Newton's gravitational law, which states that the relative degree of interattractiveness of any two bodies in the macro or microcosmos always varies inversely as the second powering, n squared, n to the second power, of the respective arithmetical distances intervening. Have the distances and increase the interattractiveness fourfold. So somebody will say, interesting tetrahedral ideas, but don't power law relationships and power relationships amongst numbers in the real world empirically demonstrate a quadrangular accounting? So here's 6.75, the quadrangular accounting. So here's how people quadrangularly account for squaring. They say it's like the game Battleship, or Connect 4, or chess, or Risk. You just do m times n, and that's the number squared. That's multiplication. But also, it turns out that in 2 and 3 dimensions, you can also do triangular accounting. Here's 1, 4, 9, 16, and the exact analog for 3 dimensions. So in other words, that number to the second and the third and the nth power is a relationship that has to do with geometric scaling rather than uniquely identifying the cubic world as a singular explanatory or descriptive factor of reality. So numbers being raised to powers is about the shape of space and the shape of the numbers. It's not about cubes or squares. So it's better to say that a number is being raised to the second power than it's being squared, even though I literally said it when I was reading it. But that's just like going upstairs and downstairs, when really it's instairs and outstairs. This is just language that helps us or prevents us from kind of grasping what synergetics is about and what it means for us. So 8. All right. So 8. TET is the minimal, geometric, and topological system, so it provides an interactionist model. All right. So here, this is figure 6.7 in cosmography. So given underlying order in superficially seeming randomness law, the number of interrelationships x of a given number n of something is x equals n squared minus n over 2. So this is kind of a relationship people who have studied network theory or any sort of graph theory will know this. This is like the number of edges in an undirected graph, because basically it's the number all by all minus the ones that each one can make by itself. So that's kind of like effectively taking one of the nodes n off the table, and then you're going to double count, so you divide by 2 so that you don't get double counting. But if it was a directed network, then it would be just n squared minus n, or you could even have just simply n squared. So that's represented on the left column here. If you have one point, you have no interrelationships. AB has one edge. A, B, BC, and AC, 3 points, make a triangle. So there's 3 edges. 4 points make a tet. Look at that. That's the minimum 3D system. Here's where our tet comes into existence. But note that there's kind of a few concordant representations. So as we get more and more events, there just gets a denser and denser web. And the number of interrelationships, it turns out, doesn't just scale numerically according to this n squared minus n over 2 sequence series, but also it's the number of kisses in this stack of oranges. With each one that you add, each layer you add, adds an even larger amount of interrelationships into the system. So here's that 2n squared, but it's not squared. But it's calculating in numbers being raised to powers in a way with this differential. And so this is just to suggest that TETs and the kind of structure that they build as they get into the high frequency zone, large TETs, many layers, gives us maybe some insight into the law of large numbers and mean field approximations. So we know about the Gaussian, how many random variables multiplied or added together, for example, will give certain types of Gaussian variance. So maybe here's a geometric component to that. And also TET let us model things that seem parallel, as well as things that seem densely packed or ragged or sharp. Because you can just imagine these packings of kind of atoms, packings of oranges, it can be a really narrow stack. But we can still think of the TET as being the shape of that stack. And then again, what this point was supposed to be about, 8, this interaction model, that because we can think about the points, the vertexes as events, and the edges as relationships, we get this minimal topological and geometric system. So point, line, and plane, just like Kandinsky, point, line, plane are topological, but they're not geometric in the real world, because even the canvas or the paper in the real world has 3-dimensionality, ergo it's geometric. Okay, 9. So TET is a mnemonic, so memory device for phase change. This is one maybe we've talked about before, or maybe it was in trim tab, but there's a few ways that TETs can associate. So if they're touching at one vertex, it's a like gas phase. So let's see, trivalent bonding of figure 637. Trivalent bonding of vertexial spheres forms rigid structures. At C, gases are monovalent, single bonded, omniflexible, with inadequate interattraction, separatist, compressible. At B, liquids are bivalent, double bonded, hinged, flexible, with viscous integrity. At A, Rigids are trivalent, triple bonded, rigid with highest tension coherence. So note that double bond and triple bond are not, it's not the carbon bonds you learned about in chem class. This is synergetics bonding along a point, edge, or plane, 1, 2, or 3 bonds. So it's not trying to use the turf of carbon bonding. It's just giving us a way to think about some of the properties and constraints and restriction of degrees of freedom of gas, liquid, and crystal. So that's pretty cool. Maybe cubes do that too, but it's cool to see TETs do it. 10. So 10, again, the Kandinsky. TET structures of tunable frequency, so that means of different size, like different Lego size, can make points, lines, and planes. So the TET alone is a point. It's like the tiniest little granule of sand. So that's how it becomes a point. But how do we get lines, things that look like struts, or things that look like planes, like pieces of paper, in a TET world? And so here's how people would solve it in the cubic world with just a row of blocks, kind of like a skyscraper or like a Jenga block. But remember that from earlier that there's this TET inscribed in the cube. Figure 673, cosmography. So we're going to inscribe a TET in every cube, both of them, both directions. So that allows to build this tensegrity mast. The minimum structural system in the universe, the TET, can be tensegrity structured. A linear growth of the tensegrity TET becomes a tensegrity column. Because carbon fiber is most probably constructed in exactly this way as a tensegrity TET column, it is demonstrably the strongest and lightest column structurally producible. The column and its method of assembly are shown in 6.47. So again, there's this concordance between the move that out of the way, between the 6 faces of the cube and the 6 edges of the TET. And then every cube has 8 corners and every TET has 4 corners. Every cube contains 2 TETs, A, B, C, D, and W, X, Y, Z, because each of the 6 faces has 2 diagonals, the positive and the negative set. So the diagonal on the cube, which is root 2, 1.4, allegedly, is the edge of the TET. So TET edge is irrational in the cube world, but as we saw, vice versa as well. So it's kind of like 2 cultures, cube and TET cultures, and they're irrational to each other. But we can build long, thin tetrahedral masts, as well as rows of them for planes. So what does that look like? This is a nice figure. Figure 649. So tensegrity masts as struts. Miniaturization. I'm not sure how to say that word. Approaches for atomic structure. Miniaturization. Someone help me. But it's kind of showing like an investigator looking at these little tensegrity struts, and they look like they're rods. They look like they're compression elements in the geodesic dome, but actually you look at them with a magnifying glass and they're tension elements. So this is just a huge important point, which is that tension at one scale, spatially, can be compression at another scale. So tension keeps the structural integrity of this mast. It's the tight wires that keep it up like a spine, but at another level of structural analysis, this can be a compression element, even though we know that the mechanism of structural stability is tension. So that's really important for nesting, which brings us to point 11. So that's one way that nesting happens in synergetics, but also 11, which is TET. Tensegrity analysis gives a natural model of function, constraint, and nesting. So here's figure 646. A system within a system. Tensegrity TET with a tensionally positioned central ball suspended at its center of volume. Central ball completely restrained in terms of all 12 degrees of freedom of all individual systems. Note that the 6 solid compression members, that's the 6 rods here, 6 edges, are the acceleration vectors trying to escape from the system at either end by action and reaction. Whereas both ends of each would-be escapee are restrained by 4 tensional wires, 2 short and 2 long, while the ball at the center is restrained from local displacement, torque, and twist by 3 triangulated tension wires, also tangentially affixed to each of the 4 corner balls. So, kind of like the energetic desires of the TET allow a system to be nested inside of TET. So we saw TET as minimal system, but now there's going to be another system nested inside of TET. That's one point. Because TET is so minimalist and austere as a system, it allows nesting as well as, of course, the lateral composition of systems really well. This is another also restriction of degrees of freedom based argument for first principles using a TET. So here's a TET. Here's a radiation of a universe and a disintegrating event, which is like rays going out into the universe. And then here's gravity. That's a closed event. And so it's sort of like a tripod. It implies a triangle of structural bounding. Like if you had a rope that was a fixed length and you had a tripod that was just trying to spread out, it would stop and make a TET when the legs had spread out to the length of the rope. And then if there was more force, more weight pushing down, then the rope would snap. Or if there wasn't enough force pushing down to make the rope expand out, it wouldn't be a TET either. So this is kind of like a first principles approach. And then if you had just a triangle, like 2 connecting pieces, then any gust of wind would knock it over. And if you had just one, it would also fall over. So it's the minimal stability system to have that tripod pushing its weight out and then the rope on the ground. So that's one argument, minimal structural stability. Here's another one. Here's that one stick. Can go in any degree of freedom, any direction. 2 sticks, any degree of freedom. You restrict their degree of freedom, but they still have multiple ways they can fall. When you restrict the degrees of freedom of 3 sticks, they can still fall in certain ways. And then when you have all but one edge, it can still flap and unflap. So you need that last edge to get structural stability, and you don't get structural stability before then. So it's like necessary and sufficient. There's nothing even close to that in the cube world. So if there's a cube proponent, I'd love to hear your thoughts on this slide. All right, so 12. 12 is TET great circles eliminate the need, not the existence of pi. So this is probably going to be contentious. And so it's not that pi doesn't exist as an asymptote or even a calculable number with some special properties. Here's what it says in the text. Figure 653. The 4 great circles of a sphere, the spherical tetrahedron divides area of sphere into 4 triangulated areas with base times altitude, eliminating the need for pi. So it's not that pi is being eliminated as a concept. We still get to have it as a concept, but we don't potentially need to use it in calculation because these 4 points are where the 4 great circles intersect. And they happen to be the points of the tetrahedra. So we have equations that relate the relationships of those points in a polyhedral coordinate system rather than a spherical or a radial coordinate system. So we're just going to have different corrective numbers, but things are going to be calibrated to the TET, to so-called 60 degrees, rather than calibrated to some other number. But it turns out that they divide well into each other, so it might not matter. Okay, so maybe there's more to say on that one, but let's go to 13. So 13. TET, just one, is hiding inside of every closed object or system. So here's figure 655, Angular topology independent of size, cosmography. Equation of angular topology. S plus 720 equals 360 times xn, where S equals the sum of all the angles around the vertexes, and xn equals the number of vertexes or crossings. So this is true for a line as well as a tet, which is if you take the number of vertexes and then you sum the angles around the vertex, and then you multiply the sum of angles by the number of vertexes. So these are all regular shapes. So the each vertex is going to be able to just be multiplied just like the other ones. They're part of the same symmetry groups. It turns out that when you get basically the space that an unfolded shape would have minus the shape that a folded shape has, you always get 720. So boom, 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 720, 720, 720. And it turns out that that relationship, figure 654, tetrahedral mensuration, means measurement, applied to spheres, that 720 difference between basically the internal and the external angles, it holds even when the number of angles summed is like 300,000 in this case, 292,000. So there's a tetrahedra inside of all of these polyhedra because it just turns out that the shape that has to get taken out topologically to make a closure is 720 degrees, double twist. It's a tet. So 720 happens to be the angular sum of a tet. So it's just an interesting note. 14. So tet accounting is clean for angular or general properties, as well as specific measures like length and volume. So we saw from the orange stacking that there was a clean accounting of volume or mass. But here in figure 656, tetrahedral mensuration applied to well-known polyhedra. We discovered that the sum of angles around all vertexes of all solids is evenly divisible by the sum of the angles of a tet. The volumes of all solids may be expressed in tet. So we have the sum of angles is divisible by the sum of angles of a tet, and the volume of solids is also divisible by a tet. So that divided by 720 is angular, and then there's a volumetric component as well. So think about graphic designers and video game designers and trying to make cubes describe reality or look realistic. But potentially, we have an accounting system here for length, for edge length, for volume, and for angle, all in terms of tet. So, sounds pretty cool. And then here's the 15th and final point, which is tet invariance group equals best invariance group. So, this one I'm not as sure about, but maybe somebody who's listening knows more. So here's figure 680, constant properties of the tetrahedron. And so it gives several constant properties. So check out cosmography to learn about some of these invariances that are related to moving the points around or pushing them through other shapes. And then here's one of the interesting invariances just to give an idea of what these are. Constant unit volume progressions of asymmetric tet. In this progression of ever more asymmetric tet, only the sixth edge remains constant. Tetrahedral wavelength and tuning permit any 2 points in universe to connect with any other 2 points in universe. So here it's like 2 points here, and then those 2 points at the same distance. You've got a transmitter and a receiver over here. This is going to still have the same volume of 1, even as the shape changes vastly. So that's pretty interesting. But the tet invariances are the best invariances. That's it for the tet rhetoric. Again, that's only 15 points, and there's probably 1,500. But that's what was just being used naturally in the 6th chapter of cosmography. So it just shows how dense the tet web is woven by Bucky, et al., et al., et al., and just how deep geometry is. In the second part of Synergetics, number 12, we will go to Synergetics section 200, narrative exposition of spherical accommodation. But before that begins, we will go back to slide 1082. So in Synergetics number 10, we talked about this sequence of, or I guess 11, not in video number 11. We talked about this sequence of considerations. So basically, 9 things to keep in mind. 9 considerations about synergetics. Energetic vectors, Avogadro's energy accounting, angular constancy, isotropic vector model, close packing of spheres, diametric unity, vector equilibrium, concentric polyhedral hierarchy, and synergetics. And then we ended with this cool image about like modern geometry research and ancient and everything in between. So that's kind of where we're at. And then the next slide is the 10th consideration. So the 10th consideration is so different from the first 9, and so much longer that it demanded its own segment. So here it is. This is Synergetics section 200, narrative exposition of spherical accommodation. So just a quick reminder, spherical accommodation means kissing spheres. We're going to say unity is plural and at minimum 2. Unity is going to be the distance between these 2 spheres. So that each are going to have a radius of 1, but then unity is going to be plural and going to be valued at 2. So this is the area we're going to be talking about. Consideration 10, the spheric experience, energetic reality, accounting versus abstract cubic accounting. So we're going to be contrasting fake news, cube, Minecraft world with TET world, spherical accounting, 4D, all we see. 202. In Synergetics 1, sections 262 through 966, I developed the first, second, and third power values of my numerical factors for converting the XYZ coordinate system's edge lengths, square areas, and cubical volumes to my 1927 discovered synergetic system's unit vector equilibrium, vectorial edge lengths, triangular areas, and tetrahedral volumes. See table 963.10. Here's the table. It didn't convert too well. RIP. So this is just saying that there was some conversion factors necessary for the first, second, and third order relationships for line, face, area, and then volume. First, second, and third order relationships had to be corrected in TET world as opposed to cube world. It just had to be done. 203. The synergetics coordinate system, in contradistinction to the XYZ coordinate system, is linearly referenced to the unit vector length edges of the regular TET, each of whose 6 unit vector edges occur in the isotropic vector matrix as the diagonals of the cube's 6 faces. We also recall that the 8 corners of the cube are defined and structured omnitriangularly by the symmetrically interarrayed and concentric pairs of positive and negative tetrahedra. So that's why there is a good first section on the rhetoric of the TET and on cosmography, because a lot of those topics we saw about cubes and TETs. So that relationship between the 6 vector edges and how those on the TET are part of the IVM, and then how that relates to the 6 faces. Just vital. 204. Since the cube face diagonal is the edge of the 6 vector edged 4 planes of symmetry tetrahedron, and since Synergetics finds the unit vector edge tetrahedron to be the simplest structural system in the universe, the tetrahedron's vector edge logically becomes the most economically primitive, simplex module of relative length in Synergetics coordinate systems of explanatory reference. Thus, the tetrahedron's unit vector edge of unity 2 is manifest as nature's coordinate primitive length module for assessing second power triangular area, 2 to the second power equals 4, as well as assessing the vector's third power tetrahedral volume, 2 to the third power equals 8. These areas and volumes become the logical unit of areal and volumetric reference in accounting the relative geometrical area and volume values of the entire hierarchy of primitive, concentrically congruent, symmetrical polyhedra, as these naturally occur around any vertex of the isotropic vector matrix, and that matrix's experimentally demonstrable maximum limit set of 7 axes of polyhedral symmetries, which 7 symmetries, section 1040, accommodate and characterize the energetic special case formalization of all great circle gridding. So it tied in a lot of TET ideas here. But basically, this part is saying the edge of the TET should have a value of 1. This should be our point of reference. Why would we make the edge of the cube value 1? Let's just call this 1. Now, if anyone says, well, you can't just choose, it's kind of like 1 inch versus 1 meter or 1 centimeter. Like, we can have the same ratios, but choose what 1 is going to be. And then we're going to have this integration with unity as plural and at minimum 2 to have the kissing spheres relationship. So we're going to get first edge, second areal, and third volumetric relationships scaled relative to cube world because we're basing it off of the edge of the TET rather than the edge of the cube, which, as we've seen, are inscribed in one another. The TET is inscribed in the cube. So this is kind of an interesting little disclosure by Bucky. 205. The Synergetics hierarchy of topological characteristics as presented in table 223.64 of Synergetics 1, which was contracted for with Macmillan in 61 and published by them in 1975, discloses the rational values of the comprehensive coordinate system of nature, which my 60-year exploration discovered. In 1944, I published a paper disclosing this rational system. At that time, I was counseled by some of my scientist friends, who were aware that I was continuing to make additional refinements and discovery, that premature publication of a treatise of disclosure might result in the omission of one or more items of critical information which might later be discovered and which might make the difference between scientific acceptance or rejection of the disclosures. Reminded by those scientist-artist friends that we only have one opportunity in a lifetime out of many lifetimes to publish a prime science reorienting discussion, I postponed publishing a comprehensive treatise until 1970. At the age of 75, I felt it could no longer be delayed. So this is kind of cool. It's just like Bucky giving a little personal history here and saying that Synergetics 1, giving a little time frame here. So it took 14 years from the book contract to the book being published for him to come out with Synergetics 1 with Ed Applewhite. And then it's part of a 60-year journey, and that he got feedback from scientists and artists and fusions of there above. And then also that he sees this Synergetics hierarchy of the topological characteristics to be his key contribution. So that's pretty cool. But there's more to say. So Bucky, 206. The 11th hour publishing of Synergetics 1 coincided with my busiest years of serving other obligations over a period calling for a vast number of tactical decisions regarding the methodology of producing what proved to be a 780-page book. Typical of the problems to be swiftly resolved are those shortly to be herewith recounted. The accounting also discloses the always surprisingly productive events that ensue upon mistake-making that are not only discovered and acknowledged, but are re-explored in search of the significance of the mistakes having occurred. So this is just awesome, Bucky, learning by doing, and just saying, yes, it was part of my 60-year mission, but also we totally rushed it out the door, and we were learning by doing. 207. Because the XYZ coordinate three-dimensional system values are arrived at by successive multiplying of the dimensions, volume in that system is inherently a three-dimensional phenomenon. But in Synergetics, the primitive values start holistically with a timeless, sizeless tetrahedral volume unity in respect to which the cube's primitive value is 3, the octahedron's relative timeless sizeless value is 4, the rhombic tricontahedrons is 5, and the rhombic dodecahedrons is 6. In synergetics, when time-size special case realizations enter into the consideration, then the only interrelated to one another primitive volumes of the synergetic hierarchy are multiplied by the frequency of the edge modulation to the third power. Since innate primitive volume is a base times altitude three-dimensional phenomenon, and since all the synergetics hierarchy time-size realization volumes are inherently six-dimensional, I was confronted with an exploratory tactical quandary. Absolutely thrilling. What is his tactical quandary? The problem, 208, was to arrive at the numerical volume value for the sphere in the synergetics hierarchy, and the dilemma was whether I should apply my synergetics volumetric constant to the first power or to the third power of the XYZ's coordinate system's volumetric values, as arrived at by the conventional XYZ coordinate system's method of calculating the volume of a sphere of radius vector equals 1. This operation is recorded in section 982.55 of Synergetics 1, where I misconceptualized the operation, and without reviewing how I had calculated the constant for converting XYZ to synergetics, redundantly took the number 1.192324, which I assumed, again in mistaken carelessness, to be the third power value of the synergetic conversion constant. And I applied it to the volumetric value of a sphere of unit vector diameter as already arrived at by conventional XYZ reference mathematics. The conventional XYZ coordinate volumetric value for the volume of a sphere of radius 1 being 4.188, which multiplied by 1.192324 gave the product 4.99. A value so close to 5 that I thought it might possibly have been occasioned by the unresolvability of tail-end trigonometric interpolations. Wherefore I tentatively accepted 4.99 as probably being exactly 5, which if correct was an excitingly significant number, as it would have neatly fitted the sphere into the hierarchy of primitive polyhedra, section 982.61. My hindsight wisdom tells me that my subconscious demon latched tightly onto this 5 and fended off all subconsciously challenging intuitions. 209. But what I had mistakenly assumed to be the third power synergetics constant was in fact the ninth power of that constant, as will be seen in the following list of the synergetics constants raised to synergetic constant raised to varying powers. And here's that list. 1.192324 is s to the ninth, and the value to the first is just 1.019, and that third power is 1.06. So a devastating disclosure by Bucky, but it's going to have a interesting conclusions. What is happening here? So he's really walking through for himself and maybe for us about how he made a mistake that was just so vast and unambiguous, and also how that relates to the way that the XYZ thinking pervades our thought. So, as in the previous slide, the three-dimensional values of volume, so like the cube having a volume of 1. So it has an edge length of 1, and then, wow, it has an area of 1. Oh, and it has a volume of 1. That is amazing. That's the SI system. However, volume is inherently three-dimensional. And so there's some sort of third-dimensional scaling relationship that's hidden in the cube having both an edge length of 1 and a volume of 1. So in synergetics, when we renormalize volume to tet unity, we get some other relationships. So Buggy's trying to do some calculations, and he accidentally does he cubes the cube. He's already working in a way where you don't need to add this third power in, but he adds the third power in And so he gets up to the 9th power. And so that then is confirmed by his belief that like integers are really cool. So sometimes when he was very close to an integer, he would really latch onto it. Not every time, but many times. So Bucky makes a mistake in Synergetics 1 because how sweet it would be if spheres fit into this picture so cleanly. So 210, skipping, so 211. Whatever the workings of my subconscious may have been, the facts remain that I had erroneously concluded that the 5 was the tetravolume of the sphere whose diameter was our unit vector, whose value was 2. In due course, I received a letter from a mathematician, Ramsey Campbell, whose conventional calculations seemed to show I was wrong, but I was not convinced that his conventional results were not also erroneous, insomuch that they had been cubically arrived at rather than tetrahedrally referenced. So, you're computing in the wrong paradigm, bro. You can't disprove me, says Bucky. 212. At this point, a young associate of mine, Robert Grip, who was convinced that I was misconvinced, and who knew that I would alter my position only as confronted by a physically demonstrable evidence, made a gallon-sized, water-holding tetrahedron and a sphere whose diameter was identical with the prime vector length of the tetrahedron's edge. The water content, the volume of the sphere, was indeed 4.43 units, 0.57 less than 5. So that's classic Bucky getting that experimental demonstration right in front of his eyes of something and that updating his mind in a way that thoughts didn't. And then the idea of like how many marbles or beans or water would fit in a shape, that kind of volume conservation is really cool. And it's a cool technique. 213. The cubically arrived at spherical volume A of a sphere of diameter equal to the unit edge of the XYZ coordinate system's cube is 4.188. To convert that spherical volume value A to that of sphere B, whose diameter is equal to the diagonal of the face of the XYZ system's cube, we multiply the volume of the sphere A by the Synergetics hierarchy volumetric constant. Okay, pause here. So it's the difference between a sphere with a radius of 1 versus root 2. So that's one world. If you're in cube world, the edge is 1, and then the diagonal is root 2. But if you're in tet world, where the tet is kissing spheres, and so unity is plural, and at minimum 2, so let's pick 2. So its edge is 2. And then if its edge were 1, this would be root 2 over 2, which a lot of trig students probably have seen. But because the edge is 2, this is just 2. So it's the difference between a sphere, again, that goes through this left point and this point. That's with a cube's edge or with a tet edge. What's the ratio of the volumes? Well, you get it by the Synergetics hierarchy volumetric constant, which is obtained by taking the synergetic unit VE vector linear constant 1.0198 and raising it to its third power or volumetric dimension. So that number cubed, which equals 1.0606. Multiplying this XYZ system's cube edge diametered A sphere's volume of 4.188 by the Synergetics volumetric constant of 1.0606 gives us 4.4429, which is the sought-for volume of the sphere B. I thanked Mr. Campbell and acknowledged my error. So it's kind of a cool story because it's like maybe the real Synergetics was the truth we knew along the way because he had the right numbers, he had all the right intel, but he got so locked in with that integer value. But then when he just did it right and had it presented to him analytically and physically, he came around. I then said to my mathematical associates, Robert Grip and Chris Kitterick, that there is no single item that more effectively advances research than the unblocking of our thought processes through experiential evidence of a previously held erroneous assumption. Wherefore my intuition told me that my error may have been stubbornly clung to because there might have been something very important to be discovered in this region of investigation, there is possibly some enlightening significance in the fact I had intuitively applied, and again, forsaking the first correction, had doubly reapplied my third power synergetics conversion factor to an already three-dimensional cubic volume quantation measurement, which on the occasion of these retreatments had erroneously seemed to me to be as yet 3 powers short of the minimum primitive realizable somethingness. Why did I think as I did? Why was I puzzled? I was not confused about arithmetical operations per se. We conventionally arrive at the area of a square by multiplying the square's edge length by itself, and we arrive at the volume of a cube by multiplying its edge length times itself twice. That is, we identify the square's area by the second power of its edge length, and we identify a cube's volume by the third power of its edge length. All that seems simple and clear, until we discover that the cube does not exist and cannot exist until it has at least 3 other observable attributes: weight, duration, and temperature. Given the quantitative inputs for those coordinate factors, the cube as yet fails to exist because as calculated it is now solid. And physics has discovered and proven that no such solid phenomenon exists. Wherefore the cubical domain has to be substantially populated by atoms, which have a variety of interspacing and interpositioning behavioral patterns. So, pretty fascinating way to conclude that little story. Bucky tricks himself. He pranks himself. He didn't take the already cubic dimensional scaling relationships into account. Silly Bucky. And it is at the very heart of some of the deepest questions. For example, if we want to have the French Revolution SI system, so 1 centimeter on the edge, it's 1 centimeter cubed of volume, it has 1 gram of water, it has 1 area of centimeter squared on painting. That's the cube world. When we take the plunge into TET world, not just do the values change, not just do 1 need to be rescaled and area and volume, but the scaling relationship changes because the surface area to volume of different shapes is different. So the scaling relationships between a number and the number times itself and the number times itself a second time, the first, second, and third power relationships, those relationships need to be re-understood. But as we talked about earlier, it's possible through triangulating and tetrahedronating numbers, you can get what you get at with squaring and cubing. So it's a cultural preference. Maybe it's one that favors one side or the other. I think it's a discussion that's still ongoing. But so fascinating how Bucky is emerging from the cubic paradigm, still makes legacy errors, gets the experimental demonstration from an older and a younger colleague, the older colleague with a theory and the younger colleague with a practice, kind of like a Hermann Hesse novel. And then this more general point that when we rethink and reinterpret, that's when our research can advance the most. And then Bucky investigating his own thought process and just realizing that when you have a TET first world, you're getting at the essence and the kernel of structure. Cubes, which can only exist as at least a tertiary derivation of a TET world, which we talked about earlier, they must take on these different scaling relationships if you want it to make sense. But also, in a TET world, any cube is composite, so it's going to have different relationships as well. So, just one more time to say that in a TET world, the cube is the weirdo, and vice versa. And so there's some extremely dialectically interesting things happening in geometry, and the conversation is still happening. So that was Synergetics, live stream number 12. The themes and the spirits were reformat, partition, and listen. We talked about the rhetoric to the TET. We looked at Richard Ramsey's awesome key ideas of Bucky. Then we talked about the 15 of the infinite number of points around the rhetoric of the TET. And then talked about Synergetics 200, narrative exposition of spherical accommodation. So I hope you enjoyed this time that you spent and appreciate the attention. Thanks for checking it out, and let me know if you ever have any suggestions or comments or questions. Thanks. Bye.